My name's Chad Royston, Senior Refining Consultant, Bryan Research and Engineering. And I've been here about 4 years. Been helping clients the world over with crude distillation modeling, with reactor modeling, with, of course, what is our heritage, gas processing and gas treating as well, and the way that that ties into the refining industry. So this will be a refining focused webinar this morning. And let's go ahead and launch into the agenda. Okay, so we're going to discuss how to define a crude in Promax. And if you guys have a second to just to text in specifically, if you've never seen Promax before, if you never used Promax before, or if you're an expert at Promax, that would be helpful. You can go ahead and do that right now, and I'll be taking a look at that. Please feel free to text any questions you might have directly to me, just right now as we go, and I'll try to address those as we go. So we're going to take a look at some of the very basics in Promax regarding oil speciation or oil specifications. And I see we do have some frequent users as well as some new users. So I think today will be a good cross-section of fairly approachable material from a basic standpoint, and we'll try to hit that early on and then move into some more meaningful discussions as we go. So we'll take a look at how to define an oil, or in this case, we'll be looking at crude distillation. And then we'll be taking a look at potential yields from a crude and how to determine what those are. So TPP splitters will be used. That's one tool that we offer in Promax. And then we'll take a look at distillation gaps, distillation yields. Specifically in this case study will be for distillate. So the way that we're going to review today's material is meant to be very general in the sense that you can apply it to different oil cuts and find your own way to apply it to your process. Okay. As a bonus, we'll take a look at determining how to estimate your diesel sulfur distribution, or really more generally your crude oil sulfur distribution, and derive an estimate using a Promax oil speciation tool. So okay, so here we have a couple unnamed crude assays. Do we have, and what I was hoping is if you guys would mind shooting me your vote as to which one's the heaviest. Which one is the heaviest crude here? The one on the left or the one on the right? And they are all for the one on the right as being the right choice. How do you determine that? So anytime you're looking at a crude assay, you certainly want to take note of the units. This one is in degrees Celsius. And, a quick way is to take a look maybe at the 50% point and determine where that boils at. So you say 50% of the left crude A, boils close to 200 degrees Celsius, okay? Whereas the one on the right is nearly 400 degrees Celsius. And so when you are reviewing these crude assays and you're able to assess them graphically, you should be able to ultimately have a really good feel for what that particular crude curve is going to bear. This particular one on the right that we said is the heavier, certainly, by the time we're at 500 degrees Celsius, we've only distilled 65% of it. So it's a much heavier crude, and we would not expect to distill a great deal of that crude, certainly in an atmospheric column. And so to really process the crude on the right here, you would need to further process it in a vacuum unit and then conversion units downstream of that, of course. So this is one method of information gathering that we would have. And in Promax, we probably enter this in a tabular format. So it's pretty common to have this information both in a table or an Excel spreadsheet, as well as graphically presented to you, either from your coordination group, your product quality group, whoever's in charge of your crude purchasing, or if you are the crude purchaser, you probably have these types of assays in your system. So moving on, how do we define a curve oil in Promax? Okay, it's very basic. Promax skill is understanding how to enter in the requisite information to define a curve oil, as we call it, which is just that. It's going to be a collection of oil cuts based on a boiling curve, and the minimum amount of information we would like to include is also the specific gravity with that. So taking a look at this slide, what you'll see in blue are the Promax inputs, okay? So whenever you enter in information into Promax, you'll know it's been user input if it's in blue, okay? So this particular crude assay has been entered in with the assay here and the specific gravity. Let's just go through the rest of the agenda, and then we'll get into Promax here. The second thing we're going to do is we're going to take a look at a tool we have called the TPP Splitter that's going to allow you to separate a curve oil based on boiling points. And we'll take a look at why that could be useful and some of the limitations to that, but should be a nice tool to estimate yields, okay? Take a look at the diesel spec and our full crude model. Does everyone here in the web session have a pretty good idea of the way the atmospheric crude unit operates? Again, we're going to be operating the crude unit at minimal pressure, the goal being to elevate the temperature of the crude and flash off as much of it as possible in the flash zone, where the preheated crude enters on what would be stage 21 here in this model. And all the vapor will rise up through the column, and that's all the heat input for the column. The one key difference, crude column versus some more common columns, is that there's going to be no reboiler, but all the heat input into the system is going to be enter in with the feed. So we're going to rise up through the column, and we're going to cool off the column at certain places. We could just have an overhead condenser to provide all the reflux for the column, but we're oftentimes providing cooling at intermediate stages of the column for various reasons, and pulling off products, intermediate products from side cuts on the column. So this particular model, we're modeling a Caro cut, a diesel cut, which is just commonly known, or also could be known as distillate, and AGO for atmospheric gas oil. AARC at the bottom would be our atmospheric reduced crude, okay, or residuum. That would then be fed typically in a medium conversion, high conversion refinery to a vacuum unit. All right. Then we're going to take a look at a scenario tool. So for our Promax users today, who's got experience with the scenario tool? What it provides is a way to systematically approach a case study and to develop trends based on inputs into the model and recording outputs of the simulation. So it'll historize the results of several Promax simulation runs, as well as automate those changes once you've set it up. So I find it to be a very valuable communication tool to communicate a lot of things that might come to you if you were just to explore the model yourself without a scenario tool. And I know myself, I'm guilty of that. It's nice to get into the model and you can make changes to it to understand it yourself. And I think sometimes the real value is finding a way to visualize what those changes are and the important ones are, and communicate those to your team. Okay. And assuming we have time, and I think we should, we'll take a look at oil speciation tool. That's part of our autokinetic reactor suite. and how we would estimate diesel sulfur distribution, species, etc. And the nice thing about that is tease it up nicely to go into a reactor model, part of our autokinetic reactor suite. So this is our crude model I was discussing with you. Now, before we model any crude system, it's going to be important for us to define an oil, okay? So this particular model has already been solved. So for those that are new to Promax, when a model is fully green, that's our general convention for a solved model. Okay, when I go up to the top here and click on my execute box here, clear calculations, it'll clear the calculated data and it returns the system to blue with maroon streams, okay? And hit execute flow sheet and it'll solve, okay? Just a few notes about Promax for the beginners here. We'll try to keep this brief because you'll pick it up and we have a lot of, I would say, more advanced users in the session. Is the project viewer to the far left really is a window into the entire project, into all the objects in the program, starting with the flow sheets where you can drill down into all the process streams that might be defined by you or outputs of the program. Energy streams, we're going to define those separately, and then our blocks. So this particular model would have a crude tower, and then it has reboilers, stripper columns. We include splitters. So anytime you have flow split off, that's going to be considered a block in Promax. And then we have calculators, user value sets, some more, I don't really call them advanced features, but they're ways to customize your program to get the results that you're after. Then we have, I guess the most important is environments, okay? This is where you define the crude oils or the components that are in your environment and the equations of state you'd like to use. And then solver summary and warnings. So this really is a window into the entire project. Now, it's not the only way you can access things. You can also just click on what you're interested in, say stream 8, and it'll automatically pull up the project viewer to what I was interested in, okay? Let's see, the other key things to note are where you get the shapes for the flow sheet, okay? They're going to be located here. You can hide that or pull it out if you want to start to grab shapes to bring onto the flow sheet. I mentioned streams and process inputs. You can just pull one out onto the flow sheet, and when you don't have any information entered into it, it'll be red, okay? Once you start to fill in the required information, that's when it'll be, the blocks will be blue or the process streams will be maroon, okay? That doesn't mean it's converged, full mass balance, mass energy balance and for a steady state, but it means it's fully specified, okay? If you need to delete something, you just highlight, press delete, okay, yeah, delete that. We've got all of our objects, unit operations you would typically expect over here on the left. Onto the execute project executes every flow sheet in the project, okay? Promax operates a little differently from some systems, some simulator systems, in that we allow the user to define the environment on each flow sheet. And in this case, we have another flow sheet. Okay, so this is where we're going to take a look at the TPP splitter. But what you'll see is you can define different environments for every flow sheet. Okay, and so it makes a really nice way to envision the material. It's really analogous in my mind to looking at process flow diagrams as you would, in a refinery for your process unit. So we often tend to model these, by process unit, if possible, or just whatever's comfortable for the eye, whatever fits on the page, in the size that you're after. So it's very customizable, but again, you can use different environments between flow sheets. You can also just execute specific blocks, if I add a splitter block, I can highlight it and just click execute block, and it'll execute that one specific unit operation. And then most importantly, or one of the most importantly, is Promax help. Pulled up, I figured I would show you guys distillation, okay? And about Promax distillation column. This pulls up a window into all the details into how to specify these systems and the principles that were used to derive simulation. So really, if you can't get the answer here, you're going to need to then I would suggest clicking contact support. And this will take you to our bre.com website. And it has a whole lot of additional information. It has information on other trainings. It has technical articles. Of course, our world-class technical support, contact information. So we're available. We're stationed here in Bryan, Texas, and available to help you over the phone, over the computer. We really want to be a part of helping you reach your process solution. Okay. All right. So just a quick rundown for those that are new to Promax. So how to define an oil. Okay. In the interest of time, I'm going to show you how one that's already been done has been specified, okay, and how you do it in Promax. All right, so for this particular model, we've entered in several different oils, okay. Before we can add oils and edit oils, let's take a look at the environment, okay. So the active environment is the environment that your particular simulation is functioning in. And this environment is called all crudes. And the first tab is going to be the property package. So this one we've selected SRK. Also common for hydrocarbon distillation would be Ping Robinson, but you're definitely going to be not requiring a non-polar package, but utilizing SRK or Ping Robinson will probably be appropriate for what you're after doing crude distillation. Okay. Secondly, we have components. And components is where we add specific species from our library. You'll notice here we have over 11,000 that have not been entered into this particular environment and are available here. And in general, when you see boxes like this in Promax, you'll have potential to input on the left and what has been installed on the right. Okay, so this particular model has installed some light ends, okay, over here on the right, as well as water. And then oil is crude A has been installed. So there are some other oils that are available and have been defined, but they are not in the environment. Okay. Crude A is the crude that's being distilled here in this particular model. All right. So going to oils, where was crude A defined? Well, crude A was defined as a blend of several different oils. So it'd be very common for you in the refinery to be sending several different types of crude, perhaps, into the same column. In this case, we're modeling it as equal parts Hibernian, Bonnie, Cusiana, and Qua Ebo. All right. And that is what we've called crude A. All right. This allows you to make changes to this and ultimately end up with one set of based on the mix. Okay, so you're going to have oil cuts defined as crude A, and the temperatures are the volume average boiling points for these crude cuts. Okay, so this particular model is going to be a total of, let's see how many cuts we had. 29 plus 8 plus 2, so 39 cuts. Okay. Now that is customizable. You can make changes to the number of cuts that you're utilizing to define a particular oil. Okay. The default is going to be 25 degrees Fahrenheit for every crude cut below a TPP boiling range under 800 degrees Fahrenheit. Okay, that we found that gives a good balance between solve time and granularity of data. So, like I said, it is customizable, and you can certainly increase the crude cuts even in a specific temperature range that might be important to you. Okay. All right. So how did we get here? And go to curve oils. So I mentioned curve oils were a mixture of these four oils, and how were they defined? Okay. So we'll open up one here, and all that's going to be needed to enter in information for a curve oil is going to be the crude oil assay. Okay. And we would like to inform that information with the specific gravity, which is going to help us make estimates about physical properties as well as the chemical composition, so PONA estimates, Watson K factors, etc. What's going to be very important with entering in information in Promax or in any model for that matter is making sure you have the right assay type. So this particular model is a TPP curve been entered in, and the TPP curve is on a volumetric fraction basis. It could also be entered in on a mass basis. It's very common to get these also for different oils as the SIMDIS or 2887. The D86 is very common as well. And Promax can provide curves for all of them. It's just important to know the basis that you're entering in the information, because that will affect your results a great deal. In this case, we're entering in a specific gravity, and Promax will give me a default number of oil cuts based on the temperature range. Would have any impact on the product specs when we change the number of cuts and temperature range for each cut? Yes, I think it would make changes. Certainly, we're talking about yields today. It will make changes in yield, certainly for a TPP splitter. That's one reason you might want to use more cuts in a specific region. If you're interested in a specific point spec and the oil in a specific range. So the question is, what is the optimum number? The default is probably used by 95% of people that use Promax. So again, the default is going to be 25 degrees Fahrenheit up to 800 degrees Fahrenheit in temperature range. So as you see here, you've got 32 to nearly 807 degrees Fahrenheit, and that's going to equate to, what is that, 700, nearly 775, okay, divided by 25, and you'll get 31. That's how the numbers of cuts are derived. Now, once you have set your number of cuts, you will then have physical properties for each cut, okay? If Promax doesn't know or have a good estimate out of a certain range, then it's going to start to highlight those items and say, at this point, estimating the flash point for, say, oil cut Cusiana at 48.6 Celsius, estimating the flash point, you might want to take it with a grain of salt. Now, every simulator is just that. It's providing best estimates given the state of the art. So I like to say that every simulation is wrong, but then I qualify that and say, well, every instrument reading you have in the plant is wrong. So it's just a question of how useful it can be. So when we're looking at our data here, we do highlight information in yellow is okay. We're starting to extrapolate here farther from our correlations, but we're going to give you a number, an extrapolated number here. Red would be a stop kind of convention of, hey, this number, you might want to find some laboratory data for it if you're going to be basing a process design on it. In addition, we also have the plot. So we'll have a boiling curve plot, specific gravity, molecular weight, viscosities at different temperatures, okay, high and low. So we do offer some information here on the curve oil. That's it. It should be fairly easy for even a beginner to do to specify a curve oil in Promax. All right. Now, using the TPP splitter. So the question is, once you have a crude oil defined, light ends. So we have several different options on light ends. One is to not allow specific species to be used, but just utilize oil cuts as defined. But one can substitute specific species for the crude by utilizing either your own data. So you could enter in your own data here and include the species that are in your environment. This particular environment, I believe, say had ethane. You can enter in specific species and you can supply light in, for example. So if I say I know I have 0.3% by volume ethane for some strange reason, okay, then I can apply that and it's going to alter my crude oil at that point, because what it's going to be doing is it's going to be recalculating my curve oil and substituting ethane into that composition for crude A. Okay. And so what it does is it's going to change all my cuts. If you notice, my cuts are different now. And so I really am altering my crude composition in the way that it's defined throughout the program. All right, so let's go to the TPP splitter and let's pick an oil. Take a look at what you're able to do with that. We have a TPP splitter here. Whenever we're developing a new model, one thing I've already done is establish what I want my cut points to be here in the TPP splitter. As you notice on the flow sheet, my block is blue and the streams are maroon. Okay, so that means I've got a fully specified block and I'm ready to calculate it. So what is my first thing if you're looking into a new model is what's the environment? So we'll take a look and see what we've got. We've got the all crudes environment, again, SRK, and I've got crude A available to me as an installed oil. Let's go ahead and add a couple other ones. We'll add Cusiana, QI. All right, so now I have two more oils available to me to specify a particular stream. So I open up my crude stream. Any process stream in Promax will need to have the process conditions specified, and that's typically most commonly done with temperature and pressure, as well as a rate. Okay, this is a steady state model. A process stream will need a rate associated with it. Most typically in the crude models, we'll be utilizing standard liquid volumetric flow rates. Matching overhead gases, we'll use standard vapor volumetric flow. So, domestically, commonly used million scuffs a day, 1,000 barrels a day type units. So now that you know the conditions and the flow rate, you also need to know the composition. Okay, so those are the things that are absolutely necessary to make that stream maroon. This information here, did I enter all this in? Now, I said when you enter something in the Promax, it turns blue. It says it's user input, right? Did I sit here and type in all of these? No, of course not. All right, so I specified from this button, I did that rather quickly. It's the specify button here, okay, in the bottom left of this window. Okay, everyone see that? And what that allows you to do is, of course, you can make changes to individual oil cuts. But what I want to do is install, and I have to check this button here, install a previously characterized oil in this stream. All right, so I have crude A, and then I have the two that I just added to my environment, okay? The Cusiana and the QI, all right? So let's say I take Cusiana, all right? What did it do? If you you'll notice it populated all of my oil cut fractions for that particular oil. All right, so I said, okay. And now I have my oil defined and it's green. Okay. That means it's solved and I'm ready to extract properties of this particular composition and flow rate. Okay. And we're calculating properties for it. Okay. Now, let's double click on my TPP splitter block. Well, where do I find that? Let's say I wanted to bring a new one out onto the flow sheet. The TPP splitter block was developed to aid with our reactor modeling capabilities. And what it allows you to do is to make quick cut points based on boiling range. And so it is available here in the autokinetic reactor stencil. And so we'll just pull one out here like so. So that's how you pull out a new block for the TPP splitter onto the flow sheet. Okay. So let's go ahead and delete that. Take a look at what we have in this one. So it's a very simple block. All right. So all we're doing is providing cut points for different stream products. So this particular TPP splitter has a naphtha, a caro, a diesel, a gas oil, and a resid stream. Okay. So what we want to do is provide cut points for where we want those specific items to be cut and execute. And we'll have yields provided in the block here that would be available to be copied and pasted, let's say, to Excel, what have you. Also, it has split those oil cuts. And so now I have a diesel stream here, okay, at 22,000 barrels a day. And my composition, yes. The question was, this is a theoretical yield. Yes, this is a theoretical yield. Okay, and so that's what I'm going to do, illustrating the TPP versus the equilibrium stage model, is showing why it's important to have an equilibrium stage model, the limitations on yield for a given oil cut in a real column. Okay, so we have our diesel defined by these particular oil cuts. So 1, 2, 3, 4, 5, 6, 7, 8 of the cuts. I think we had around 40 for the whole crude. And so these cuts are going into what we're calling diesel. And again, it's based on simply the volume average boiling point in relation to the TPP splitter set points. But it gives you a nice idea as to the specific theoretical yields. If you want to be more specific, again, you can add more oil cuts to add to the granularity of that data. How can we make a good estimate of the real yields? Well, that's a great point. I think what this is important to do is to understand an approach to theoretical yield. So depending on the process, it can be a very handy tool. So, we're using it for crude here, but it can be used for stabilization. One of the best uses for it that I see is, say, reformate stabilization, where you want to drive off, C4 minus, for example. But it has, like I said, other uses just to help you understand the particular amounts of oil available in each temperature range. So some people are really good at seeing it directly from the crude assay, which is why I wanted to get a feel for how well everyone was able to do that today. If you want to put a specific number on it, I think this is a really good tool to do that. Now, is it possible to achieve this yield and have a perfect separation? Well, of course not. So let's move on to the real distillation column, the equilibrium stage model, and take a look at what that would entail. We have our crude column system here. And this system, learning how to fully specify this is the result of a typically probably 6 hours of instruction. It's a day's worth of our BRE 211 Advanced Refinery Operations course. So regrettably, I can't go into all the details how to specify this model, but certainly can do so on an individual basis. Anyone that is interested in learning more about specifying this model certainly can do that at a later time. Let's go ahead and execute this flow sheet. I changed my crude here. I've got another question. I see there is no need to use recycle. I made one CDU simulation and use them because I know all inlet streams have to be defined. Okay. So your question was how to do it without recycle. Yes, the crude column does not require a recycle. It's part of the block, so you don't have to specifically use the recycle blocks. That's correct. I didn't mess up my environment here, playing around with this. Okay, is everyone able to see the green column system now? Okay, how about now? So what we wanted to take a look at was diesel yield for our diesel product here. How are we defining that? So in this particular model, we were taking a look at diesel and we were specifying it with a diesel cut point, an ASTM 95% of 625 degrees Fahrenheit. Okay. Now this was being set actually on the stripper as opposed to the diesel draw, which is a little lighter. Okay, which makes sense because the stripper is going to be removing light ends from my draw from the main column and helping us meet our final product rundown spec. Okay, so again, we've all up to speed with what the diesel, or excuse me, with what the crude unit is, and we'll be pulling off different products from locations on the column. And what we wanted to look at today was the impact specifically of our pump around duty on our diesel yield. You know, we say diesel yield optimization, diesel yield maximization. Certainly, you're going to be dependent on your crude assay. You can't take more than exists, okay? Which is one reason I wanted to show the TPP splitter to give you an idea as to what the maximum theoretical yields might be for the oil given boiling range. So how does that work dealing with an equilibrium stage model? Some of the quick specifications for the column, for the crude column, if you haven't done crude column distillation in Promax, is the necessity for VLLE. Okay, we have lots of steam being added into the system, both in the bottom of the main column, gas oils, as well as stripping steam utilized in the product strippers that are being fed back up into the main column and being condensed in the overhead condenser. So having the VLLE flash type selected is critical. Stages, this particular model, we've got 3 psi delta P across the column. Okay, and so we've established the pressures for each individual stage. Now it's important to remember here that we are dealing with stages and not with trays. When I model a process system for a customer, what I try to do is give the appropriate number of stages to model the plant behavior that we're able to see based on both the product draw temperatures and the product assays. And that's going to enable you to determine how many stages might be necessary to model a particular set of trays, but typically it's more trays are needed than stages. Specifications. So this is the clearinghouse. This tab here is a clearinghouse for all of our information and constraints on the model. You'll notice we have, for this particular model, we're setting a flash zone temperature at 650 F. You could set a crude feed temperature. Those are highly dependent on, or the flash zone temperature is highly dependent on that. So it's very, very close to the same number. And then we're setting 95% cut points for our products. So that means we're controlling the heavy end of our products in this particular column here. So we've got the naphtha, the AGO, and the diesels, 95% cut points. Once we have fully specified the model, the degrees of freedom calculator at the top should equal 0. So this is a nice feature that allows you to tell, oh, okay, I've fully constrained my system. I'm going to get an actual answer here. Without that, if it was possible to over specify, it would certainly lead to a lot of problems relative to specification of the model. So we have a green column. Okay, so what does green mean, everyone? What does the weight column mean? The weights are available for the ones that you've selected as a specification. So if you enter in specifications here, you are able to adjust the weighting. My colleague is weighing in here. Do you use the weighting? They're not available for ones that do not have it. He says that they might be available if you choose allow over specification. If I can, what I would like to do is take a look. I had a scenario tool already set up. Okay, I'm going to attempt to export the scenario that I built prior column that I was operating here. If I can export this. Hopefully this works here. Okay, so to do the case studies we're talking about, what we'll need to do is add Excel workbook here. So when you add an Excel workbook to your file, it's going to be important not to close it using the close button. If you close an Excel workbook in your Promax file, it will delete it. Okay, so it's important just to minimize it. All right. So go into the Promax tab here. You'll notice the scenario tool button. Okay. So we're going to click that. Can everyone see the scenario tool come up? Okay. So what we wanted to do was determine the impact on pump around duty on my diesel yield. Okay. So what we'll do is we'll take a look again at what my pump around duty was. So we're at 70 million BTUs an hour. So I was interested in, let's say we're at 70. Okay, that's where we're currently at. And this, we'll call this LPA pump around. We're interested in what happens when we reduce that. Okay, so let's make sure we have our units associated with this. All right, so I'll have this as an input in our scenario tool. So in the scenario tool, what I want to do is add an input. Okay, so you would click add variable. Okay, and it will add one here, which is what I've added. Okay, and I want to select a range of inputs in my Excel. So what I'm doing is mapping my Excel cells to my Promax input, and they're going to be tied to a specific object in our program. Okay, this particular object being the lower pump around duty and energy rate. Okay, You'll know you properly linked it up when the units are correct. Okay, and you've found the proper Promax object. We'll get some more practice with this in a second, but I'll go ahead and click OK. Change up some of these ranges. So what we want to output from Promax is going to be diesel flow rate, diesel product, let's see, diesel product rate. So this would be the stripper bottoms, so the diesel stripper bottoms, which is going to be slightly different. The diesel 95% cut point. Diesel endpoint. This is the diesel draw temp. Okay. And let's go ahead and click run here. So if you'll notice, I've got run from 1 to 4. What's going to take place is it will input my differing lower pump around duties while exporting the information that I'm interested in. So I already noticed, okay, my diesel draw temperature was off by 1 here on the range. What this allows you to do is to tabulate data and to explore trends. Now, what happens when you lower the lower pump around? Are we expecting that to have an impact on the diesel yield? And if so, why? So it's important to qualify that. Number one is we're maintaining a diesel 95% cut point at 625. You can make changes in the column qualitatively and fix a quantity, or you can make changes to the column quantitatively and fix your quality. In this particular case, we're setting it at 625, the diesel 95% cut point. We're saying we don't want to get any heavier than that. We're attempting to increase our diesel product flow rate. Typical efficiencies is the question. So since you used equilibrium stages, what are typical efficiencies for the CDU? Would vary across the column. When in doubt, we typically use 0.7, 0.75. Now, that would be, and yes, I think they would change somewhat across the column. What's the best way to model that? Are you interested in modeling that from a design standpoint or from an existing column? Existing. So I think having a good match, initially is important. So you're going to determine what your efficiencies are based on your column performance. So the way I would do that is to take a column model and attempt to match it. If you have crude rates, different crude rates in different draws, and try to match them at different operating conditions, find a nice match there in terms of stages, and then certainly utilize an additional set as a test to see how well the match is. All right. So the question is now, could you just use the actual number of stages? Well, so you mean actual number of trays? Okay, good. I would use actual number of stages. That's going to be your best tack for these models. So once I made the sizing based on ideal stages, we need to simulate his heat and mass transfer model considering real trays. Typically, what I've seen design standpoint in my EPC experience as well as here is modeling crude units utilizing equilibrium stage modeling and not utilizing the heat and mass transfer model. So what we see is certainly we have an increase in diesel flow rate given a decrease in lower pump around. Okay. What's going on here? So let's model a couple other things. See what else we can add to the system. So what I want to add to this specific scenario tool is the AGO 5%. Okay. So we'll take Promax output. That's what we're after. We'll call that AGO 5. And when we want to select where we want that output information to go, we can use the cell selection adjustment box here. Okay. So we want the AGO 5% to fall in these cells in column G. And we'll select a Promax object. So what are we interested in? What I was interested in showing you now was the fractionation between the diesel and the AGO. So if you want to pick an item, an object in Promax, you can comb through the project tree. You can also, if you click on the stream or block that you're interested in, Promax will automatically go to that specific stream or line item in the project tree. Okay. I go into the AGO product. This particular one does not have a distillation analysis, so looks like we're going to need to add that, which is good because I haven't taught you guys how to do that yet. Cancel here and go back to our system. So our AGO product. When you want to develop a distillation curve for a process stream, you go to the Analysis tab, click Add Analysis, Distillation Curves, okay? And typically we do 21, so it'd be 5% increments. And most commonly, get this information a lot in D86, sometimes SimDist, but D86 is probably the most common. All right. So we're going to hit solve, and we'll have a table of data. So have a light tail on this and a heavy tail on this gas oil. Okay. And we have a plot tab, so you can get an idea graphically of what that particular product draw looks like. Okay. So what is the AGO 5% point? Well, now that we've determined through the analysis what that is, it should be available to us now in our scenario tool. Okay. So I think I had already had this defined. Should be good to go now. Okay. All right, let's add it. So we're going to add the AGO 5 again, and we're going to select Promax object, click on that stream that we're after. It's going to make me calculate it. Might make me calculate it before it's available to me. Let's go back to that again. I was looking to add was we had our AGO 5% here, okay? And this is the AGO diesel gap, which is simply the AGO 5% minus the diesel 95%. And what this would tell you is that you do have a great amount of diesel still in your gas oil. And that's really no surprise. It's why often that material diesel can be extracted either from the vacuum system or there are other ways to solve this problem, and you're going to be limited in your fractionation efficiency in this section. But as you see, is when we do decrease the amount of pump around in this system, what we're able to see is, of course, as the pump around duty goes down, the diesel draw will go up. And part of that is we are having some better fractionation between the gas oil and the diesel. Still really poor in the sense that it's an overlap. Okay. So what we want to do is be in the positives for a really good cut. Okay. But the other way that we see what's happening is we can look at our draw temperatures. So we have a diesel draw temperature. So this is the temperature that the diesel is extracted from the main column. And as we lower our lower pump around duty, our diesel draw temperature went up. Okay. Our Caro draw temperature went up. And our AGO draw temperature went up. But what happened to the deltas? Okay. Our heavy delta. So that is that. That is the difference between the AGO and the diesel draw temperatures. Okay. And it stays pretty static around 60. But you'll notice the light delta, which is the difference between the Caro draw and the diesel draw temperature, has gone up by 10 degrees. Okay. So we are seeing a different operation of the plant here, as is evident by a decrease in the overlap, which is showing better fractionation efficiency. And then we're asking about tray internals and that sort of thing. The glitch jet flood has increased. Okay, so what we're seeing, and this was for tray 17, actually stage 17. This is indicative of greater vapor traffic or greater traffic on that tray, and that really makes sense because what the pump arounds and a lot of these pump arounds were designed to do was to help energy efficiency and to actually decrease furnace firing on our crude charge by utilizing really high temperature heat integration. There's no waste heat here. So we'll make sure that this particular scenario tool is available to use. Like I said, graphically, you are able to see increased diesel draw through better fractionation efficiency in that range. Now, you are subject to several constraints in doing so. Anybody know what those constraints are off the top of their head? So you've probably got at least three, but they're numerous. Okay. What are your constraints in doing this? How far can you lower some of your pump around duties? Okay. So, of course, you need to have an idea of what your traffic is on your column and your liquid loading and your vapor rates, and that you're not in a potential flooding situation or entrainment situation that would impact your fractionation efficiency. But from a heat and energy standpoint, there's a couple things. One would be the impact of a reduced pump around duty on your crude preheat. So you might, a real constraint on your system might be the inability to preheat your crude if you have reduced your pump around duty significantly. Okay, so that's one. Condenser duty is going to be one. Okay, so assuming you're operating the column on temperature control on your overhead, which is certainly very possible, you are going to have to create that reflux somewhere else because what's happening when you reduce your lower pump around duty here, let's say your lower pump around flow rate's the same. What it means is that you're returning liquid to stage 17 that is less subcooled and will condense less vapor in that region of the column. So you'll have more vapor traffic traveling up the column, and it will be condensed elsewhere. So if it's your own temperature control, where is that going to take place? In the overhead condenser. So you might have condenser limits as well. So a lot of these crude units have been retrofitted to utilize these pump arounds for a reason, and understanding how your condenser requirements play out and what your constraints are on the column are important. Not only that, but you're going to generate more vapor traffic, so you might run into some flooding issues at the top of the column if your column isn't size large enough. So there's a lot of things to consider and just if you're even able to do it, but certainly understanding the give and take, okay, between a localized pump around and its impact on the overall fractionation and the yields for a particular side product is important. So the scenario tool will help you quantify what those gives and takes are. So would you guys like to, I did run longer than I anticipated. Would you guys like to see the oil speciation? You have time for that? How would I do this quickly, let's say for a diesel? Okay. So, again, I'm just looking for a rough estimate here. What I want to do is I'm going to create a new flow sheet. And I'm going to say add flow sheet. Okay. And I'm doing this so we can create a new environment. Okay. So we're going to create a new environment. And we're going to select SRK is fine. Select that equation of state here. And let's go ahead and name this the oil speciation environment. And what components do we want? Do we want to enter in the crudes? Okay. Well, what we want to do is get an idea of our speciation, of our sulfur speciation. So let's take diesel hydrotreating. Okay. And let's enter those in. Okay, so we've got a lot of components, and that's one reason I want to do this on another flow sheet. Okay, yeah, so we have 394 components, and so these are actual chemical species. Okay, and so we've defined it, we've given an equation of state, given the components. Click OK. And now we'll assign that environment to this flow sheet. We'll call the flow sheet oil speciation as well. All right. All right. So how do we do this? Well, one thing I want to do is take a look at my diesel product here. So there's two ways to transmit data, let's say from my crude unit to this other environment. One would be to determine what the distillation curve is. And the other one would be to use a cross flow sheet connector. In this particular case, we have our distillation information by D86. Okay, and we have 0, 195, 5, 426, just going to write down a couple of these distillation points to utilize. A lot of material boiling in the 500-degree range. That's fine. So I've got my distillation from my crude unit, and I'm going to pull out an oil speciation block. Okay. If it's not available, you'll need to check for it here, which will then include it here to the left. And I'm going to pull out an oil speciation block right here. Every oil speciation block originates a process stream. So it's a little bit different from other blocks that have a stream entering it, a stream leaving it, or multiple streams leaving it, etc. It's going to originate the information in the block. Because of that, it'll just have one stream leaving. So it's a little different from some of the other blocks in Promax. Double click here, and we'll take a look at the required information. So we'll just say, 100 degrees, 10 pounds gauge. And one thing we didn't talk about was conversion factors. If you guys don't use them that often or have to go online to convert easy things, don't forget that you can do it in Promax. If I don't want to enter in MCFH, I'm going to say MBLL or BLD. Okay. As long as I type the units directly after my number, it's going to automatically change my units when I import that data. Okay, which is really nice. And then I'm going to enter in the distillation curve. So it's doing an oil speciation is not unlike defining a curve oil. Okay, the only difference is instead of ending up with a curve oil with different cuts that have been defined, we're going to end up with specific species. For IBP, we're going to use 195, 426 for the 5. Just enter this information in here. All right. So very important to this is knowing that the species that I've installed in my component list in the environment are of an appropriate range to define the distillation curve that I've entered. So we have made that easier on you by calculating what it is. So the species boiling point lower boundary minus 258. So it's probably hydrogen is in this environment, which makes sense because this environment would probably then be used for a hydrotreating type simulation. Species boiling point upper boundary 839. Okay, so I'm well within that boundary. The one thing I don't have for this is an API gravity. Now this is a D86. So notice I don't have the right assay here, so I'm going to change that. Okay, that's important. And I need a specific gravity from the other page. So my diesel product gravity, let's see what that was. 31, very, very light. Okay, it's hardly diesel, right? 31.7. Okay. Okay, 0.86. That makes sense. All right. Now, if you don't have a PONA, we can utilize the Riazi correlation to develop one. Of course, if you want to do anything with any sort of usefulness, other than just have a general idea, it's probably best to have a specific lab analysis of this. A lot of times, PONA information is available on the crude assay by cut. So you might even have it for your diesel cut. You just have to go check. The next would be sulfur mass fraction. Again, we're interested in sulfur species and our sulfur distribution in this particular oil cut. And what common sulfur mass fraction would we be looking at here? Obviously it depends on the oil. In might be as high as 1.2. So you're saying 10,000 parts. Okay, so it's by weight. So let's put 1.2 in here. Now, the other thing that we will utilize here is on the process detail tab, would help you speciate it based on some things that you might know. Like this is the default sulfur distribution scale. Now I happen to know that for a diesel, the default's low. Okay. So I'm going to put it at a 2, but what this is a scalar quantity that fits the peak of the sulfur. And the higher the number, the more it's going to weight those sulfur species and the heavy components of the oil, which is what you would see in real life. So more importantly, we have species overrides. So species overrides allows you to set specifically the species mass fraction for any species in your component list. So oftentimes you might have that information, say for a mercaptan or for some other type of species, but you won't know it for everything. And so we do allow you to customize that and help match what you do know, and we fill in the blanks for what you don't know. So at this point, we're blue and we're maroon. Our stream's maroon, our block is blue, and we'll execute the block. So let's see what we have here in terms of species. Of course, we have our hydrocarbons as well as our sulfur species all the way into the C24 range. So these are have been grouped by carbon number. So both hydrocarbon and sulfur species as well. So by the time you get into like C17 benzothiophenes, for example, this is something that you're going to need to hydrotreat to remove from your diesel. So this gives you a really good idea as to exactly the type of hydrotreating you would need in terms of your pressure and hydrogen requirements by modeling this stream for HDS utilizing autokinetic reactors in Promax. Hopefully that's a nice little tool for you to experiment with. Like I said, it's nice that it's customizable. You can shift the peak of your sulfur to match what you have. You can override our correlations with specific lab data. So it is very powerful in that you can customize it how you'd like to use it. Yes, this is an approximation based on certain correlations, but it's a good starting point, and we've found it to be very very useful for defining those sulfur species. In addition, you can utilize this stream subsequently in a distillation to determine where certain the amount of sulfur in a cut of a particular stream. So you could do it for a whole crude unit if you'd like, or a whole crude oil. So it's a nice little feature. Well, looks like I've taken the full time. Do we have any more questions? I see one here. How does it perform in the field versus plant data based on your experience? Yeah, well, we have had good matching of plant data. We've primarily used this function for matching sulfur speciations for naphtha, caro, and diesel cuts. I think it's designed to go a little bit heavier than that, but generally you mentioned 397 components. That seems to be pretty taxing for most people's computing power. So I think we're in a good spot right now to do this type of work. Certainly for naphtha and caro and diesel as well. So I think I'd treat everything on a case by case basis. Like I said, we're happy to help you guys utilize that feature and get a project up and running if that's something you're interested in. All right. Well, I really appreciate your time, and please let us know what you'd like to hear about in the future. If there's other things you'd like to learn more about that we didn't touch on long enough. Again, these of different skill levels, and so I think if we feedback on whether it was too elementary or too complicated would be valuable. And so that'll help us cater to these webinars in the future. Like to keep doing these, really show you the capabilities in refining for Promax.